that mode. Okay. So I'm going to talk about how we measure distances in astronomy, from very close distances to nearby stars, all the way out to the farthest galaxies. I'm going to talk about the different methods that we use and where they came from, a little historical background. I think a lot of amateur astronomers don't know all these methods or don't know much about them. So I thought this would be a good lecture to do, just so people might understand what these different methods are and might be able to answer the question if they're ever asked, well, how do you know how far away that guy is, or how far away that star is, how far away that galaxy is? When you're done listening to this, then maybe you can answer that question if someone asks you. I always start off with a slide of humor. I've done this myself. Left the lens cap on. Okay, so as I said, this is a question I get asked. Even when I'm doing star parties, outreach events, I'll get asked this question because we'll say this cluster is so many thousand light years away, or this star is this many light years away. Someone will ask me, how do you know how far away it is? And so then we have to explain. So I think a lot of amateurs don't know how to answer that question. So like I said, that's the purpose of this talk. I'm going to talk about these different methods. I'm going to try to avoid the math as much as possible. I will have a little bit of math, but nothing too complex. And so what I'm talking about is what's commonly referred to as the distance ladder, because there's different methods used for different distances. As you work out, you're using different methods. So they call it a ladder. So I'm going to go through this ladder from closest to farthest, basically. And like Pete, if you've got questions, just shout them out. So trying to figure out the distance to the things in the sky is nothing new. I'm quite sure the ancients would look up at the sky and wonder how far away the stars are, how far away are the planets, how far away is the sun. I mean, even the early Persians had at least figured out that the stars were farther away than the planets and the moon. And how did they know this? It's because they were able to observe occultations where the moon would pass in front of a star, or the moon would pass in front of a planet, or sometimes they'd see a planet pass in front of a star, like Mars would block out a bright star, or Jupiter. And therefore they knew at least the stars were farther away. They had no idea how far away. They just knew they were farther away. It means the moon was closest. The moon was closer than the planets were closer than the stars. That much they had figured out. It wasn't until you got into the Greeks, when the Greek civilization was in its prime, that you started getting what I'd call logical attempts using math and science to try to estimate the distances to astronomical bodies. And in some cases, they were able to do it. They were able to estimate the distances to Mars, to the moon, to the sun, and things like that, but without the use of telescopes. And some of these estimates were not bad. So we're going to talk about some of these Greeks who did this. I'm not going to go into a biography of these people because a lot of these names we've covered in the past, and that's not the purpose of this talk. I'm just going to mention who they are and what they did. We all know who Euclid is. He came up with basically modern geometry, and he gave us the geometrical principles that allowed us to use trigonometry as a way to measure distances. the method that we call parallax is trigonometry. It's basic trigonometry, and he's the one who came up with the principles behind it. Aristotle. Now, Aristotle is not a name that we normally think of when we talk about astronomy. He's known as a philosopher and a big thinker, and a lot of other things in Greek history, but we don't normally think of him as astronomy. But as it turns out, he did some very interesting work in astronomy. He wrote works on astronomy, including a work where he estimated the distances to the planets using trigonometry, using something like parallax, and got reasonable answers, considering. And he also wrote a paper where he came up with basically what's called a Copernican model for the solar system. Now, he was laughed at, and most of the other philosophers of the time dismissed it. They didn't believe the sun was at the center of the solar system, and so his great work on the Copernican model never got much traction. But he did some interesting work, and the important thing, the reason he's included in this lecture, is because he came up with estimates for the distances to the planets using something very similar to parallax. And his distances, while not perfect, were within a factor of 2, which, considering, that's not bad. Then there's Eratosthenes. This guy is one of my favorites. He was a peer of Aristotle, mathematician, student of the sciences, basically. He's the guy who computed the circumference of the Earth, and he got it pretty accurately, within 5%. And he estimated the size of the moon and the sun, and he got that pretty accurately too, within a few percent. And the circumference of the Earth is important here because that's going to be used for parallax measurements. And then there's Hipparchus. I think of him as probably the first true astronomer, in the sense that he spent most of his time observing the heavens and recording his observations. He made the first real attempt to measure stellar distances using parallax. Now, he was not able to get any kind of a good answer because he was using the diameter of the Earth as the baseline for his parallax measurements. He 12 hours, he would look at the star, and 12 hours later, he would look at it again, and he would try to get the shift, okay? But that's too small of a baseline, because we know that in modern parallax measurements, we're using the diameter of the Earth's orbit around the sun. So the diameter of the Earth is only a few thousand miles as compared to, 150 kilometers for the radius of the Earth's orbit. So his baseline was way too small. So even with his telescope, he would not have been able to measure the angles, and telescopes were not around during that time. So he was not able to get any kind of, all he could come up with is the stars must be very far away and must be hundreds of times farther away than the planets. That's the best he could do. But he at least attempted it using the parallax method. And if you don't know what the parallax method is, this is what it looks like. It's simple triangulation. You're on the Earth, like on that figure there, and you look at the star once in June, and then you look at the star again in December, and the star is going to shift positions relative to background stars. And if you can measure that angle, then you can compute the distance to the star. That's how you do measurements for close stars. And to make it some things came out of that method. The definition for the unit parsec, that is the distance at which a star would be from the Earth if you use the radius of the Earth's orbit as one astronomical unit, and at a distance of 1 parsec, the angle theta, which is half of the angle that the star would shift in position, would be 1 arc second, and that would put the star at 1 parsec, which is 3.26 light years. Keep in mind, though, that when you're doing this parallax, you're measuring twice that angle, because you're measuring the star 6 months, June and December, for example. And so you're on one side of the sun, and 6 months later, you're on the other side of the sun, and you're measuring this 2 theta angle. This angle here is actually 2 theta. You're measuring that whole angle there when you do the measurement. So if the star was 1 parsec away, what you would actually see in terms of that total parallax angle would be 2 arc seconds, because you're actually measuring twice the angle. So, but this is what parallax is. For anyone who's interested in the math, here's the math. You measure the angular shift. 6 months later, you measure the star again, and you see that angular shift with respect to background stars. You use a small angle approximation to the sine of the angle is roughly equal to the angle, because it's a very small angle. And so you can use a small angle approximation, and you can get that formula down at the bottom right, which is very easy to compute. And so you can get the distance right out, and it comes out in parsecs. Now, as I said, Greek astronomers, they couldn't measure stellar distances because they were using the radius of the Earth, which they knew Eratosthenes had measured that, but that's way too small of a baseline for your parallax measurement. Even the closest star would have had a parallax angle less than 1/1000th of an arc second. So there was no way they could measure that. Certainly they didn't have telescopes, and even if they had a telescope, I don't think they could have measured it. Parallax measurements didn't start becoming useful until the time of Isaac Newton. And at that point, astronomers had telescopes, and they knew the orbital radius fairly accurately. And so they were able to start using the orbital radius as the baseline for their parallax measurements. And they were able to measure angles down to fractions of arc seconds. And so at that point, they were able to start measuring distance to close stars. However, until the later half of the 20th century, in fact, probably until the last 10 years of the 20th century, parallax measurements basically could only be done for a couple thousand stars. Because even with large telescopes, because of problems with the atmosphere and everything else, getting angular measurements down to the hundredths of an arc second was extremely difficult. And so you could only get a couple thousand of the closest stars with the equipment that was available at the time. Finally, in 1990, the Hipparcos satellite was launched, and the Hipparcos, I'm sure I'm butchering that name. The Hipparcos satellite was able to provide accurate distance measurements for over 100,000 stars, because it was able to do parallax with a precision of milliarc seconds. So down to 1/1000th of an arc second, it was able to measure positions. And so that was able to take us out as far as a few hundred parsecs now. So now we're getting a larger area that we know distances to. And then the good one that came out was in 2013. European Space Agency launched a satellite called Gaia. The Gaia was able to provide parallax measurements with a precision of 20 micro arc seconds. This allowed the distances to go as far as 8,000 parsecs, which is basically all the way to the center of the galaxy, to the galactic center, the center of the Milky Way. And basically, Gaia provided measurements, distance measurements for virtually every star down to 15th magnitude. So that's a bigger portion of the Milky Way. Parallax is considered the first rung in our distance ladder, if you like. Yes. The Harvard Observatory computers and Mary Ann Draper. I love this picture on the left, by the way. I used it a lot in several lectures. It's a really great picture. Anyway, late 1870s, a gentleman named Henry Draper started a catalog of stars using the spectral lines to differentiate the different types of stars. He died in 1882, but his wife, Mary, on the right, continued his work for a little bit. But later that year, she basically donated all her equipment to the Harvard College Observatory, and endowed the Harvard College Observatory to continue his work. Two ladies in particular in this picture down here on the left, Wilhelmina Fleming, who is in the red circle, and Annie Cannon, who is in the blue circle, worked on this Draper catalog for a number of years. And what they got out of their work and eventually published, what we know of as the OBAFGKM classification system on the spectral classes and temperature. In 1890, the Harvard College Observatory finally published the Henry Draper catalog. Then these two gentlemen came along. These two astronomers are, I cannot pronounce his first name, Ejnar Hertzsprung, that's the try I'll use, and Henry Russell. Independently, they took a look at the stars in the Henry Draper catalog, and they picked out stars that had known distances, that is, stars that had parallax measurements out of that catalog. And they eventually came up with a relationship. They discovered that there was a relationship between the spectral classification of the star and its luminosity. Because they had measured distances, and they had the spectral classification, and they had apparent magnitudes for the stars, and since they knew the distance from parallax, they could deduce what the luminosity was, and they eventually came up that there was a relationship between spectral classification and luminosity. And if anybody doesn't know, the absolute magnitude of the star is how bright the star would appear at a distance of 10 parsecs. But anyway, this relationship was later refined over the years, and has been named after both of them, and we all know it as the Hertzsprung-Russell diagram. And if you look at this diagram, you can see that basically for the stars, there is a very tight relationship, not quite linear, but almost, between spectral classification, or color, if you like, or temperature, if you like, on the x-axis, versus luminosity going up and down the y-axis, which relates to absolute magnitude. What this allows astronomers to do is that we can now look at a star in the sky, and it can be, as long as we can see it and take its spectrum, and we can determine its spectral class by looking at its spectrum, we can place it on this diagram and get an estimate for what its luminosity should be, its absolute magnitude should be, and then we measure its apparent magnitude, and based on its measured apparent magnitude and what we think its absolute magnitude should be, we can compute a distance. This relationship allowed astronomers to basically map the Milky Way, because now they can look at stars all the way to the edge of the Milky Way, determine distances, determine where they are at various distances, and basically we can create a map of the Milky Way. Now there is something else that comes out of this too, is that we can also look at stars and determine what's called extinction, how much the star is being dimmed by gas and dust between us and that star, and that also is useful for creating a map of the Milky Way. But this HR diagram is what allowed astronomers to actually start looking at the structure of the Milky Way galaxy. The HR diagram is what's called the second rung in the distance ladder. The method they call it is main sequence mapping, if you like, where you map a star on the diagram to get its absolute magnitude. Let's go back to this picture again. Like I said, I love this picture because of the people that are in it. Henrietta Leavitt, she also was what's called one of the Harvard College Observatory computers. She's the gal in the red box there. She worked at Harvard College Observatory until her death in 1921. As part of her work for Pickering, she studied variable stars. In particular, she did a study of Cepheid variables located in the small Magellanic Cloud. Based on that study, she was able to establish a relationship between the variable star's period and its luminosity. I just made a note here. Look on the wall behind her, and there's a light curve for a variable star. One of her favorites, I think. I'm not sure. So in 1912, she published a paper where she showed this relationship. See the figure there. This is from her paper. And it showed that the periods of variable stars is directly related to their luminosity. You notice there's two lines in this plot. One of them is a variable star. So one is the minimum magnitude. The top line is the minimum magnitude of the variable star, and the bottom line is the maximum magnitude of those variable stars. And she showed that the relationship applied to both the minimum and the maximum magnitudes for these stars. And thus, if you could measure the period of the variable star, you could again map it directly to an absolute magnitude, and then you could measure the apparent magnitude by looking at the star and thus compute its distance. What this allowed astronomers to do was to look at other galaxies outside of the Milky Way, because now you had large telescopes by this time. You had 100-inch, and 30 years later you have a 200-inch telescope out at Mount Palomar. You could look at close galaxies like the Andromeda Galaxy or the Pinwheel Galaxy, and you could pick out individual stars. And so now you could look for Cepheid variables in those galaxies and use those variables as a standard candle, as a way to determine the distance to those galaxies. This was extremely important because this is how Hubble first was able to establish that at that time they were called nebula, the Andromeda Nebula, the Pinwheel Nebula. This was how he was able to ascertain that the Andromeda Nebula and the Pinwheel Nebula and these other galaxies were not part of the Milky Way. They were way outside the Milky Way's boundaries. And this is the method he used to determine that. The Cepheid variable method is called the third rung on the distant ladder. Type 1 supernova. This is a little bit different than the other rungs that I've already done. It's going to be out of order because this is a very recent one. Surprisingly enough, this is the newest rung, but not the last rung. So I'm not doing them in order of years. I'm doing them in distance order. So it turns out Cepheid variables make really good standard candles, but they can only be used on the galaxies that are close enough where you can actually see the individual stars. That limits you to less than 5% of the galaxies that you can look at, even with the Hubble Space Telescope. That was really too small of a sample to do a good calibration on Hubble's law, which is the last rung in the ladder, which we'll talk about. And astronomers tried to find something else, a better way to calibrate Hubble's law, if you like. So in the 1990s, you started seeing a lot of papers come out, mainly from astronomers in Chile and the United States, published a series of papers indicating that the type 1a supernova, the way it decayed after it reached its maximum brightness, the decaying light curve, might be used as a standard candle. Turns out that the way it decays is a very well-defined process because we understand the type 1a supernova really well. It has a very distinct light curve and a very predictable light curve when it decays. And they were able to come up with a way to refine the relationship and show that you could use a type 1a supernova decaying light curve could be used to estimate a distance to that supernova. The guy who really came up with this relationship and has published it is an astronomer by the name of Mark Phillips. That's his picture in the center there. On the left, there's a type 1a supernova in that galaxy. I don't know which galaxy that is. On the right is the original figure that Mr. Phillips had put in his paper showing the decaying light curve from a type 1a supernova. And there's a type 1a supernova decaying away, and you can see what the light curve is doing there. But type 1a supernova are often very bright. In a lot of cases, they're brighter than the entire galaxy for a short amount of time. So you can see them as far as you can see galaxies, basically. You can see type 1a supernovas. And then by observing the decaying light curve, and you do some fancy curve fitting and some other mathematical manipulations, you can deduce a distance. And this allowed astronomers to, quote, calibrate Hubble's law, because now they could look at galaxies out to billions of light years away, as long as you saw a type 1a supernova. So we try, astronomers today are always looking for supernovas because they want to catch this decay curve, because then they can get a good measurement of a distance. And it's pretty accurate. They found that it's accurate to within a few percent, as far as they've been able to tell up to now. Now, one of the things that came out of this was that this is how they originally found that the Hubble's law for the expansion of the universe didn't work, had problems. This is where they first started seeing the problems, as they started looking at type 1a supernovas from galaxies that were very, very far away, and they weren't matching up with what Hubble's law was predicting. And these are the original measurements that came out of the type 1a supernova measurements. This is where they started having to come up with theories that involved dark energy and the acceleration of the expansion of the universe. Came directly out of the measurements for here, because they didn't line up with the standard Hubble model. This is called the fourth rung. This is considered the fourth rung in the distance ladder. We'll take a step backward in time now. During the 1920s and the 1930s, Edward Hubble did a lot of work classifying galaxies, and he studied their radial velocity, basically how fast they were moving away from the Earth. He matched up his data with the distance estimates that were available from Cepheid variables, and he was able to notice what appeared to be a relationship between radial velocity and distance. So that's Edward Hubble on the left, and on the right is a sample of some redshift for some different galaxies. The spectrum on the bottom is the laboratory at rest reference, and then if you go up, you see a nearby galaxy. The lines are shifted a little bit to the right. You go farther away to a more distant galaxy, the lines are shifted more to the red. And you go to a very distant galaxy and they're shifted way, way off to the red. And that's what he noticed. And for the galaxies that you could get with Cepheid variables, because this was before the type 1a supernova was used, he was able to match up his redshift measurements with Cepheid variable measurements for distances, and he came up with the relationship now that we know of as Hubble's law. And basically Hubble's law is actually very simple in its simplest form. It's just V equals HD, where V is the recessional velocity, how fast the object is moving away from us. H is the Hubble constant, and D is the distance. And very simple. But that law, his simple Hubble's law, is what led to the development of the Big Bang theory and the expansion of the universe that we think of today, came out of that. And I'm sure all of you probably already know this, but Einstein, his general theory of relativity actually predicted that outcome, that the universe was expanding. Einstein didn't believe it and put in a fudge factor to get rid of it. He later said that was the biggest mistake. But the law allows astronomers to compute distances for a galaxy as long as you can take the galaxy spectrum, because you can just plug it into this formula and you can measure the velocity from the redshift, and you can just plug it into the formula and you'll get a distance out. But as I said earlier, the recent measurements of supernova type 1a indicates that Hubble's law perhaps is not quite as clean as we thought it was, but it's still considered the last rung in the distance ladder, because it gives us the measurement of distances to galaxies far, far away. And the figure on the right just shows you a few of them. For example, a galaxy in the Virgo cluster. You see the spectral lines there. There's a hydrogen Balmer line there, and then there's the two calcium lines, the little pair of lines right here. these lines. And then a galaxy in Ursa Major, which is farther away, it's 1 billion light years away. You see how far the lines have been shifted. And then a galaxy that's out in Corona Borealis, which is 1.4 billion light years. You see the lines are shifted farther. And you notice that the radial velocity is going up too. They're moving faster as they go farther away. Plutus, you're out at 2.5 billion light years. The lines are shifted way over here. And then there's a galaxy in Hydra that's almost 4 billion light years away. And here the K lines are almost shifted right off the spectrum into the infrared. They're well off to the right. So the Hubble's law is still used today as a way of estimating distances to galaxies. But we know that there's probably something wrong with it. So this is kind of a nice figure that I found that shows you the different methods of the distance ladder. I didn't cover the first one, which is bouncing radar off of close objects like planets. But you've got the parallax, which is for nearby stars, which is out to maybe 100 light years. You got the main sequence fitting, where you're using the HR diagram and you're fitting stars onto the HR diagram. That takes you, pretty much the whole Milky Way. You've got nearby galaxies, which you can do with Cepheid variables. You've got galaxy clusters, which go all the way out, which you can do with the white dwarf supernova, which is the type 1A supernova. And then you've got Hubble's law at the end there. So, and that's it. Questions? Comments?
Bravo, good job, Doug.
Doug, I've got a question.
Lightning, I like that. Okay, question? Who?
Doug, it's Bernie.
Hi, Bernie.
Do you know if there's a direct relationship between Z and mega light years?
Say that again.
Do you know if there's a direct relationship between Z, which is the redshift, and mega light years?
I've
seen Z quoted as distance figures to obviously, distant.
Well, I mean, if you look at this relationship, velocity equals hd, that's a pretty basic relationship, and the Z is the redshift, right? So that's going to have a direct relationship with the V.
I've never seen a chart that had like Z and light years related to each other.
It's probably not, you probably won't see a Z related to distance, but you would probably see a direct relationship between Z and V in this equation here. Because the Z is
generally
redshift. The Z is the redshift, and that's related to the radial velocity.
Yeah, but generally the theory is also, and I think this is what Bernie's getting at, is the higher the Z, which is the higher would equate to higher recessional velocity. Generally, the relationship is the higher that number, the further the galaxy is away.
Yeah.
So it may not be quantitatively, but perhaps in a relationship, Bernie. I don't think, and maybe that has been established, but the papers that I've looked at, of course, it is kind of the math is complicated. But from my understanding, it's more of a relationship. The higher the Z, the further away. Does that equate to specific numbers? I have not seen that.
I've never seen it. I've always been curious about that.
And it's just now that they're trying to, with Hubble started it, and I think the expectation was with James Webb, because now you see the astronomers are, able to observe or have indications of being able to look at objects at high Z into the teens. I think like Z's of 7 or 8 were somewhat limiting up till about maybe 10 years ago, maybe 15 years ago. But I think that's starting to grow, and they're starting to see these higher numbers. I don't know how high it can go, because like you
say, Bernie, I know there is a direct relation. There is an equation that goes from Z to V to this recessional velocity here. There is an equation that goes from Z to V. Because that's how they measure V, is they look at the redshift, the Z number. There is a relationship between Z and V, and then you can see here from once you got V, you can go directly to D.
Yeah,
So
I'll
there
keep,
is
I'll keep looking at,
Yeah.
hopefully I'll run across something someday.
But I can tell you this, the relationship between Z and V is not linear. Because
No, definitely not.
it's spectral.
And also, I believe with some of the stuff from Webb, the highest Z value they have right now is, I think, 13.1.
Right.
Which is about I want to say, coming close to between 300 and 500 million years after the Big Bang in terms of age. So very young galaxies.
Pushing it way up.
For context, it took about the first 300 million years of the universe is opaque to us because of ionization. The universe was too hot for light to travel through it and had to cool down a little bit. So I don't think we'll see anything from Webb crossing that 300 million year old barrier. For that, you have to go to the cosmic microwave background.
So I have a question or an
Go.
observation. So back to your star party. If you're out at a star party and you say the Andromeda galaxy is 2.5 million light years away, isn't that right?
Whatever.
And somebody said, and you have a student say, well, how do you know that?
Well,
So you could say,
Tell
well,
them- you
Paul
can tell
figured
them-
it out.
tell them Cepheid variables.
Yeah, Cepheid variable, but like, because it just depends on how much detail they want,
Yeah.
I guess. You can tell them you can figure out distances with using trigonometry, which would probably turn a lot of people off, or that they've discovered ways to figure it out. Depends on how much detail they want, I guess.
Parallax is
Basically, if somebody were to come up to me at a star party and say, and if I said, okay, that star is like 40 light years away, and they say, well, how do you know how far away it is? I'd say, well, we can measure it with parallax, and I would tell them real quick what parallax is. But then if someone says, like you said, how far away is the Andromeda galaxy? And I say 2.5 million light years, and they say, well, how do you know that? I would say Cepheid variables, and I could explain to them what the thing is with Cepheid variables. And then if they talked about, galaxies that were a lot farther away, then, you can go to Hubble's law.
So to give kind of a more down-to-earth explanation for those that do engage in star parties, the way you can explain parallax is tell someone to hold one of their fingers up in front of their eyes, in
Yes.
front of their face, and
Look at it with the
close
right
one
look at it
eye,
with the left eye, and you'll
and
see
then
it's
close the
different.
other eye, and you'll see that your finger will move slightly.
Yes,
That's parallax.
correct. And you just say what astronomers do is they use an observation at one time of the year and then look at it again 6 months later. And that baseline is 180 million miles. Any other questions?
You think there's a possibility of a future presentation on the Z versus V?
That would probably be a little bit much for this group. That gets into some
kind
heavy
of-
math.
Yeah, that
Not
gets
exactly
into the heavy
amateur.
math, because I remember doing that math in graduate school. I remember computing recessional velocities off of redshifts. Yeah, that involves some math. I don't think that would be appropriate for a fundamentals group.
Maybe you need another special interest group for physicists.
Remember, this is an amateur astronomy club, not a
not an amateur physics club.
Yes,
No,
well,
but we
and
have quite a
not-
few people in the club who understand a lot of that stuff. Like my
and
husband, you know.
I'm not saying they don't there. I'm just
Yeah.
saying that it's hard to digest. It needs a
Yeah.
lot of background to it. And in
People-
general, I like to think we try to keep these presentations to around the high school level, and that's certainly pushing it into the senior undergraduate versus early graduate school level.
I mean, this is fundamentals interest group. Those formulas that take redshift and compute a radial velocity from it are all available in the textbooks, and are certainly, you could find it online if anyone really wants to know.
Thanks.
Hey Doug,
Yeah,
how do you suppose they measured the angles back in Eratosthenes' days without benefit of telescopes or photographic plates or whatever?
well, I mean, Hipparchus, okay, I mean, let's go back. This image that I got actually is a pretty good image. See what he's doing there? This is a painting, a diagram that I found of Hipparchus doing some astronomical observations at his observatory. At that time, this was Cairo. He was in, not Cairo, Alexandria. And he's got an armillary sphere behind him, and he's got another device, which I don't know what it's for exactly, but you see that he's looking through this long tube. Obviously, it's not a telescope. Telescopes were not invented, but he's looking through this very long, narrow tube, which allows him, he can pinpoint position of a star, and he would mark it down on a chart, and he's trying to do parallax, so he's looking for a shift. So he would look at the star at one time of night and then go out and then look at it again 10 hours or 12 hours later, knowing that he could use the diameter of the Earth as his baseline for his trigonometry. And he wouldn't see any shift, obviously, because the stars are too far away. But this is what he's looking for. He's looking for that shift because he's comparing it. He's looking at one star, and he's got another background star in the same field of view, if you like, and he's looking to see if there's any kind of a noticeable shift. But like I said, he wasn't able to come up with anything because no telescope, too small baseline.
So we assume that his instrumentation is really good in that he can record a position, and 6 months later.
He was looking 6 months later, more like 6 hours later.
6 hours or 10 hours, 12
Oh,
hours.
I thought you had to wait.
So modern days,
Because the Greeks, while Eratosthenes had been able to compute the diameter of the Earth fairly accurately, no one had computed the orbit of the Earth yet. They did not know. Like Aristotle had come up with the idea that he thought the Earth went around the sun, but he was laughed at for that. And they hadn't really computed what the radius of the orbit was. So they could not use that as a baseline for their parallax. Hipparchus used the diameter of the Earth as his baseline. He would do a measurement at one time of night and another measurement 12 hours later. Okay, and then he would use the diameter of the Earth as the baseline. So clearly he was not getting anything. He was not seeing any shift at all, because the shift, like I said, would have been milliarc seconds at most. And he didn't have a telescope, so the closest measurements he could get was probably minutes of arc. A few minutes of arc he could get in terms of an angular shift that he could see, which, like I said, they were able to measure distances to planets, to some of the planets, because that's close enough where you could get a shift of a couple of minutes of arc. And they were able to do that. They were able to measure the distance to the moon and the closer bodies, but not any stars.
You may have mentioned this, Doug, but how accurate were their measurements to the planets?
some of them were pretty good. Not all of them. In a couple cases, they got within 10%.
Not bad.
But in some of the other planets, they didn't do quite as well.
think
But
it's
they had
Saturn's.
estimates. They had estimates.
Take it Saturn and Jupiter were the outliers given.
Yeah. Yeah, they had a good estimate for Mars. That's the one that was, I think, 10%. But yeah, as they got farther away, of course, it got harder.
I think recession threw them off a lot too.
But considering that they didn't have telescopes, I think they did quite well. And that they didn't, also considering that they didn't understand Newtonian mechanics, or, they didn't understand the orbits. They did rather well with their distances. Eratosthenes' estimate of the diameter of the Earth was a few percent. Okay, I'm going to stop sharing.
And thank you very much, Doug. Before we wrap up for the evening, any other questions or comments before I dismiss? Thank you all very much for attending. I don't have any announcements about what's going to be on the table for next month. I need to get with the other presenter and sort that out. So look forward to that in the next month's club bulletin. Not club bulletin, the next meeting agenda I send out. So thank you, everybody. See you in a month.
Good job, guys.
Thank you. Take care.
Night.